The limit is basically the intended value of a function. So take this graph as an example. If the values of y equals to fx can be brought close enough to L by taking x close enough to a with x being less than a, then the limit of the function f of x as x approaches a from the left is L. And here, if the values of y equals to fx can be brought close to r by taking x close to a with x being greater than a, then the limit of the function f of x as x approaches a from the right is r. If the values of y equals fx can be brought close enough to L by bringing x sufficiently close to a from both sides, then the limit of the function f of x as x approaches a is L. The main thing to remember when checking to see if a limit exists is, if the limit of the function f of x as x approaches a from the right is equal to the limit of f of x as x approaches a from the left, then the limit does exist. And if the limit of the function f of x as x approaches a from the right is not equal to the limit of f of x as x approaches a from the left, then the limit does not exist.
Hi, my name is Catherine. I'll be talking about continuity. So continuity is the condition of being uninterrupted without breaks or irregularity. So a function f of x is continuous at a particular point when x equals a if f of a is defined and if the limit of f of x as x approaches a equals to f of a. So if this property is true for all points, then in the domain of the function, then the function is said to be continuous over the domain. So a trick to know if a function is continuous is if it can be drawn with your pen or pencil without lifting it up from the paper. So there are three conditions for continuity. So the point has to exist, the limit exists, and the limit on both sides of the point has to be the same. So the example here of this function is a simple linear function, and it's continuous. There's no holes or gaps or anything. So there are three types of discontinuity. So the first example, we have f of x equals 1 over x minus 5. So obviously at x equals 5, there's a vertical asymptote. So it's in this graph, there's a discontinuity at x equals 5. And so this is the graph of that function, and that's known as an infinite discontinuity because the function just keeps on going, never touches the asymptote. In example 2, g of x equals x squared minus 36 over x minus 6. And when you simplify that, you can cross off x minus 6 from the denominator and the numerator, and you get x plus 6. However, when x equals 6, there's a hole because you can't divide a number by 0 because that's undefined. So that's the hole there at 6. But since it's only discontinuous at that specific point, it's referred to as a point or removable discontinuity. And the last example we have is h of x equals absolute value of x over x. And then you break that up into two parts. So when x is greater than or equal to 0, you have x over x, which is equal to 1. And then when you have x is less than 0, you have negative x over x, which is negative 1. So in this case, when x equals 0, there's a discontinuity there because it equals to 1 for greater than 0, but it also is equal to negative 1 when it's less than 0. And there's a gap here, there's a jump, so that's called a jump discontinuity. So a thing to know about a point or removable discontinuity is that it can be removed by redefining the function at that specific point that has the hole. So for this example, at 6, if there's a hole, you can just redefine that point by adding a point there. And so that means it can be repaired by filling in a single point. But for a removable discontinuity, it's one that a limit exists but does not equal to the value of the function at that point. So the limit, the intended value, which is the limit, is 12, but the point that we filled is about 7. So the limit does not equal the point, but that's how you solve the point discontinuity.
Okay, so my name is Zaha, and I'll be talking about differentiability. So I thought that the best way to explain differentiability is to show you a couple of rules. If something is differentiable or not. So, first, a function f x is differentiable at x if the derivative function f prime x exists. A function is not differentiable at x equals a if f prime a does not exist. Not differentiable. Also, if a function f is not continuous at x equals a, then the function f is not differentiable at x equals a. Not differentiable. Lastly, if a function f is continuous at x equals a, then the function f may or may not be differentiable at x equals a. So you have to determine that one by calculation. Okay, so the best way to figure out if a function is differentiable or not by looking at it is to take any point, point A, and see if its tangent is unique and not vertical. So for this point right here, A, the tangent is unique, there's only one of it, and it's not vertical, which means that the function is differentiable. For right here, we call this a corner point, where the two tangents meet at point A right here, and for f of f1 prime A is not equal to f2 prime A, which means that this function is not differentiable. Not different. Right here, we call this an infinite slope point, this point or this point, where the slope of the tangent is equal to either negative infinity or infinity. And this function is not differentiable because its tangent is a vertical, so not differentiable. Right here, this is called a cusp point at point A, and f prime A does not exist, therefore this function is not differentiable.